So we're going to use the method of substitution again. And again, we're going to spot what can I let u equal so that when we divide by the derivative of u, it's going to cancel with something and make the integral simpler. So I've spotted that if I let u be sine x, the derivative of sine x is cos x, so I'm going to be able to cancel with that cos x. So we're going to let u be sine x, so that du by dx is cos x. So our integral is going to become 3. In fact, I'm going to take that 3 outside the integral. You could leave it in if you wanted, it doesn't really matter. And then I'm going to leave the cos x as it is, and I'm only going to replace sine x with u. So sine squared x is going to be u squared, and that's dx. So we need to replace dx with something to do with du. So let's rearrange this to get rearrange du by dx to get dx on its own. So dx is equal to 1 over cos x du if we rearrange that. So our integral is going to become cos x times u squared times, and then we're going to replace dx with 1 over cos x du. And that works because the cos x's are going to cancel. And I knew that that was going to happen because I knew that the derivative of u was cos x, so it would cancel with that cos x over there. So now we've got our integral and we've eliminated x. Everything is in terms of u. So we're going to have 3 times by the integral of u squared du. And then we can just integrate u squared. So the integral of u squared is a third u to the power of 3. Remember, if you're just integrating a polynomial, you increase the power by 1, so u cubed, and then divide by the new power. So if we work this out, we're going to have 3 times by a third u cubed, which is just u cubed. And we need to go back to x using the fact that u is actually sine x. So we've got sine x cubed, which we'd normally write as sine cubed x. And then we just need to remember to add our constant of integration. And you can check that this is right. If you differentiate sine cubed x, you will get the function that we started with that we integrated. You would get that. So it's a good idea to check at the end. For b, we're going to do exactly the same thing. We're going to try and spot what u could be equal to, so that the derivative of u is going to cancel with something and make it simpler. So I've spotted that the derivative of x squared plus 5 is x, 2x, and that will cancel with that x there. In general, what you want to do is you want to let u be the inside of one of the functions. Because if I just let u be x squared, then I'm going to end up with u plus 5 cubed. And I can make it simpler by saying, well, let's just make u the whole of this part inside the bracket, because then I'm just going to end up with u cubed, which will be nice and simple. So I'm going to let u be x squared plus 5, so that then the integral is x u cubed dx. And we need to replace dx with du, so we're going to work out du by dx. So the derivative of u with respect to x is 2x. So we know that dx, if we rearrange this to get dx on its own, is equal to 1 over 2x du. So we can replace dx with that there. So we're going to have that. And the reason why this works is because now we can cancel our x's. And you'll know that you've used the wrong substitution in this exercise if you can't cancel the x's. In this exercise, you will always be able to cancel the x's so that you end up with a nice integral where you've just got u, things in terms of u. So here we're going to have, let's just write this out. we're going to have a half u cubed, because we've still got that half there, du. And then if we integrate that, we're going to increase the power of u by 1, so u to the power of 4, and then divide by 4. A half divided by 4 is an eighth. And then finally, we just need to replace u with x squared plus 5. And don't forget your constant of integration. And again, you can check that this is right, differentiate this using the chain rule, and check that you get the function that we were integrating.